Let's look into the flow characteristics of cyclone. The flow characteristics of the cyclone is given by Euler number here. It's a resistance coefficient which relates the total pressure drop that happens in the cyclone to the gas velocity. Okay, so this total pressure drop between the inlet and gas outlet includes the frictional pressure losses in the inlet and the outlet, as well as the changes in the direction. And this gas velocity is governed by this equation. So this is the flow rate equation, where Q is the gas flow rate and D is the inside cyclone diameter. Okay, because the cyclone will have an inside diameter and an outside diameter. So this one is the inside diameter. So this Euler number is actually a ratio between pressure forces and initial forces. This is initial force. So it's constant for a given cyclone geometry and it's independent of the body diameter. But it's dependent on the internal diameter of the cyclone. Okay, let's look into the cyclone efficiency. So the total material that is found in a cyclone is the total of fine product and coarse product. Okay, this is the total solid mass that is found in the solid exits. So the efficiency of a cyclone is defined by the solid product that is separated from the gas flow. Okay, and this equation gives you the component balance for each particle size in the solid product. So the total efficiency of the cyclone is based on the mass of the coarse product that is separated from the cyclone, and so it is a ratio from the total solid mass in the separator. Okay, and grade efficiency is the mass of solids of a particular size in coarse product over the mass of the solids of size X in the feed. So this is the ratio. So that is grade efficiency. So we can find out for each solid size how efficiently has it been removed in that particular cyclone. Let's look into critical particle diameter. So this is the diameter we are expecting to look at to define a particular cyclone, meaning to say what particle size will be efficiently separated, that means 100% separated in a cyclone. So for that we have to do a force balance for a particle size. So let's say it's in equilibrium, and it is governed by these forces. Okay, so when we make an equilibrium of these forces, we get this equation. So this is the critical particle diameter. So in theory, this critical particle diameter at this point should give us 100% separation. That means any particle size from critical diameter and above, there should be 100% recovery. But that is not the case in real situation. In real situation, there's always particles which are slightly smaller than the critical size, as well as particles that are bigger than the critical size. So in real separation process, the curve is a S-curve. So because of this phenomenon, we use a grade efficiency of 50%. We use a grade efficiency of 50%, which is X50, to define an efficiency of a cyclone. So to define an efficiency of a cyclone, we look into X50. So this X50 is also known as equiprobable size or a cut size of a cyclone. So X50 means in a large population of particles, 50% of the particles of this size will appear in the cost product. So that's how we define a cyclone efficiency. Okay, to scale up a cyclone, we use Stokes number. So this is Stokes number. Stokes number is a ratio of centrifugal force to drag force. So like Euler number, Stokes 50 is independent of Reynolds number. So for concentration less than 5 gram per meter cube, Euler and Stokes 50 is constant. So why is this 50? It's because of the X50, which defines the cyclone efficiency. So for example, in this book, we use high efficiency Stamen cyclone and high rate Stamen cyclone. So these are the fixed value of Stokes 50 number and Euler number. Okay, so once when we use the Stokes number, if we use the Stokes number, we can actually plot a curve for different efficiencies. And so we can calculate the grade efficiency. That means the efficiency to separate different particle sizes in proportion to X50. So this is the graphical representation of the grade efficiency. So this is the relative size or the diameter over D50 and the efficiency. So the collection efficiency of a particle of both larger and smaller than D50 can be determined by the ratio as given in the graph here. So we can also get the overall efficiency by plotting the collection efficiency against the particle size. So here we directly look for the efficiency for the particle size. So for like 5 micrometer, it's about 27%. Let's look into the range of optimal operation for cyclone. So theoretically, this is the total efficiency over gas flow rate. So theoretically, the efficiency of a cyclone should increase with increasing gas flow rate. However, in practice, this is not the case. The total efficiency will actually drop due to re-entrainment. So what does re-entrainment means? So when it's operating between A to B, that is the max optimum operation, wherein the dust is separated to the bottom and the gas flows to the top. But beyond this point, re-entrainment means the gas, the solids gets carried away with the gas that is leaving the cyclone, because the flow rate is too high, so there's high turbulence, so the particles gets enough energy to leave with the gas that is leaving the cyclone. So that's why we should be operating between A and B, and this A and B is usually between 50 to 150 millimeter water gauge or 500 to 1500 Pascal. Okay, so anything below A, the low limit, is like a settling chamber. So it's like if you let a gas in and you let it to settle down on its own. So it is very, very low efficiency due to the low velocity of the particles. But if it is beyond B, then it's a waste of energy, because the efficiency declines as well, because the particles gets carried away with the clean gas. There are some design consideration to look into for cyclone. So generally, high dust loadings will give us high total separation efficiency. So like dust loading above 5 gram per meter cube can actually give us high efficiency. And then for the different types of cyclones, so if we are looking at high efficiency cyclones, we are expecting high recoveries. We want high recoveries. Therefore, the inlets and the outlet orifice should be designed smaller. And if we don't mind the efficiency, but we have a large amount of gas inlet, so it should be designed with large inlet and gas outlet, and it's usually shorter. So a well-designed cyclone has got a correlation between the Euler number and the Stokes 50. So high values of resistance coefficient, so high value of Euler number will lead to low value of Stokes 50, which means low cut sizes will give you high efficiency and vice versa. And then we should also look into the abrasion points. There are two main critical points. One is just beyond the inlet opening. Once when the gas comes in at the highest velocity, so at that part there could be abrasion, and in conical parts near the dust discharge, because that's where the particles will hit the wall of the cyclone. So abrasion can happen to the equipment. And then it can also cause attrition of solids. That means the solids can break down because it's hitting the wall at a higher velocity at these points. Okay. Other design considerations are blockages. Blockages can happen due to mechanical defects like bumps on the cyclones or protruding wells and gaskets. So if there's some uneven surface or rough surface, or even there are physical or chemical changes in the solids like condensation and vapor, so it can actually build up on the surface and cause blockages. So that will affect the efficiency of a cyclone. The other factor that we need to consider is the discharge hoppers and diplex. So these discharge hoppers should be designed properly so that the particles that are separated can easily be released. So this diplex are like a pipe that allows the release of the particles for the next unit operation or for storage purposes. So if this gets stuck, so this will also affect the cyclone. And cyclones can also be operated in series and parallel for different reasons. So if let's say we have a wide range of particles sizes that needs to be separated, so that can be done in series. So large particles can be collected in the first cyclone, and a more efficient cyclone to collect the small particles can be designed at a later part. So literally the gas will flow into the first one, and this cyclone will be designed for a larger particle size, and then the gas that leaves the air that leaves this cyclone will feed into the next cyclone, and so on. Okay, so with that we can design the cyclones to cater to the range of particles size that we are looking at. And here we collect the different particle size of the dust. So this can increase the overall efficiency and overall pressure drop increase. And this series also reduce dust loading into the second cyclone. That means you don't have a very high load of dust that goes into it. The bigger particles has been removed here, so there's a smaller range, lower dust loading that goes into the second cyclone. So this avoids problems like plugging and abrasion. So we can also have parallel arrangement. So if we have a large volume of gas that need to be separated, so we can use a parallel multicyclone, so wherein the dust laden air comes in through one inlet and it goes into separate cyclones. So it gets separated, so there's one general dust collector, and the fine and the clean or the fine dust is removed at the top. So there's only one duct in and one duct out, and one collecting hopper. So which type of arrangement that is required is dependent on the process. So in the following slides, I have presented different types of parts that are used in the cyclone. So please have a read. For a cyclone inlet, so we saw in the beginning just now a simple design, which is a tangential entry such as this. But this design can also be modified for high efficiency cyclone. And then we also have helical cyclone, where this top part is slightly different. It's still tangential, but then it's not a flat cylinder, but it's slightly curved down. So that's helical entry. And then we have involute entry. So it goes semicircle and then directs it. So it's in the tangential, it goes in and directly gets into the cylinder, but this one is involute entry, so it's directed to a certain point before it circulates down. Okay, and then there are also different types of discharge system, the diplex that we were talking about. So it can just be a simple manual gate, where if you slide this gate out, then it just drops to the collector. It can be a rotary valve. So this can be a continuous discharge system. Okay. It can be a discharge screw feeder. So it screws through, okay, to free the particles from the cyclone. It can also be an automatic flap. So once it becomes heavy, so it will drop, it will open. So these particles that builds up will drop to the bottom. So this is a flap motion. And then I've also attached some monitoring and maintenance plans for cyclone. So we have daily monitoring and maintenance plan, weekly monitoring and maintenance plan, where here we have to look into the discharge valves and operations. For the daily, we are more interested in the efficiency of the cyclones. So here we look into the parts of it. And then there are quarterly monitoring and maintenance plan, where we look into the ductworks and hoods for any leaks or any component failures. And we also have annual inspection to look into the whole barrel and the tubes to see if there are any dents or deposits that can actually affect the efficiency of the cyclone. Okay, so that's all for this lecture. So let's look into the example questions in the next video.